morning, everyone. So today we will change sort of subject, and we will discuss supersymmetry breaking, which is usually shortened as SUSY, but from supersymmetry, and you put a bar like that saying that it's broken. I was thinking if it's okay with you, it may not be okay with you, but I was asking kindly if I can talk like for an hour and a half straight while you're all sort of fresh from bed and breakfast, and then go, because I'm trying to catch an early train. So I will stop at 9:45. It's quarter to 10. It's a bit yeah. This already tells you how the lecture is going to go today. Right. Okay. So right. SUSY breaking. So far, so it's the importance of SUSY breaking is both theoretical and phenomenological. Obviously, if supersymmetry has anything to do with the real world, it must be broken somehow, or we must at least come to terms with the issue that the masses of the bosons and the fermions are not the same. Remember that if SUSY is unbroken. So let us start by writing the supercharge, the SUSY computation relations in the full glory, thinking of these Q's and Q bars as operators in the Fock space of the system. So we have a theory with a Fock space with particles and multi-particle states living on it, and we have this algebra of operators, and we have seen that this algebra of operators does on the fields, say on the scalar fields, give rise to up to some constant. Now I don't remember. I think it was square root of 2i, but don't trust in that. Psi alpha. So by taking the commutator with the scalar, you get the fermion, and then you got. We use we use the trick of thinking of supersymmetry as translations in superspace to get all of these commutation relations, it's alpha, beta, f, and so on, right? And this, of course, is an anti-commutator. Okay? So this supersymmetry algebra we're not going to touch. On the other hand, if these guys, so basically, if these guys are also acting on a Fock space of particles, then when we say that SUSY is unbroken, okay, we really mean that this forms also a representation on the multi-particle states. For instance, in particular, on the vacuum, on the vacuum of your space, you have that Q bar is 0, and then you also have that if I have a one-particle state, could be a boson or could be a fermion, then if you take Q alpha of it, or Q bar or something, you also get a one-particle state. In other words, it maps one particle to one particle, it maps fermions to bosons, and it maps bosons to fermions, of course. And this is how you construct the representations of supersymmetry, right? Probably the very first thing that you do when you learn supersymmetry, the very first page of Wessenberger, it tells you how to construct the one-particle representations of supersymmetry. You take some state in a Hilbert space that is annihilated by some of the Q's, you act on them with the Q bar, and you construct a finite set of helicity states that represent your minimal representations of supersymmetry, and then you can play with all sorts of things, extended supersymmetry, central charges, and so on. Now, this cannot be. And these two things are related because you could think of generating a one-particle state by acting with a creation operator on the vacuum. And so, if this is happening, then we say that SUSY is unbroken. Now, this clearly cannot be the case in real life because this immediately tells you that there are some bosons and some fermions with the same mass. The observation comes from the fact that you, of course, P and Q commute with each other, and so P and Q square commute with each other. So, but P square acting on a single particle state is the mass square of that particle. And then clearly, if I act with Q of P square, it's the same as P square of Q. of the same particle. And this is now, if this guy was a boson, this is a fermion, this guy was a fermion, this is a boson, so you got yourself, and this reads off the mass of the other particle. So this is m squared of q of the particle. So for each state, you have a partner that has the same mass. So this is clearly not acceptable, at least phenomenologically, although it was exactly what we assumed so far in our theories. Our theories were supposed to be of unbroken symmetry. Now we want to actually keep this, but remove the fact that Susie is left unbroken by the vacuum. And sorry. There was a big important point missing here. It has to be zero. Yeah, please tell me. I actually noticed, it's incredible. I thought it was the problem with LaTeX, but it's actually my problem. I sometimes write the equation when I forget things, right? And I write, then I forget the equal sign and so on. And I always figure it's probably because it's LaTeX, you know, you don't think it looks so weird on the screen, you don't think you miss things. So I actually, this was one of the motivations, the other was laziness, to write the notes by hand. And sure enough, these things happen even when so it's really my problem. I cannot blame LaTeX. But please keep an eye on me, okay? So anyway. So we want to break this thing in so we want, basically, we would say that we want to find, it's all about the vacuum here, because once this is broken, everything else will follow, and we want to have we want to have these supercharges in such a way that they do not, doesn't have to be the same, they do not annihilate the vacuum. So we will ask ourselves for this kind of system. So first of all, let us have a closer look at how these supercharges look like. So in fact, let us take, so let X A, well A is some funny multi-index, represent all the fields that you can possibly think of in your gauge theory. So you can have scalar fields, both them and the complex conjugate. You can have fermion fields, both them and the complex conjugate. Let's throw in the auxiliary field for good measure. You can have the A field, you can have the lambda, you can have the lambda bar, and you can have the D. These are all our friends. These make up a chiral multiplet. Well, these make up a chiral multiplet, anti-chiral multiplet, and this is what the vector multiplets are made of in the Wilsonian gauge. So let's go over all of them by XA, and sure enough, supersymmetry, just like any other symmetry, will be represented by saying that I can take a variation of X. Now, this epsilon, of course, in supersymmetry is a two-component Grassmann number, constant Grassmann number, and you say that this thing here is equal to epsilon alpha delta A alpha of X, where this delta A of alpha is some funny combination of all of these things. Right? So to say that you have a symmetry, I mean, this is just the only difference between all the other symmetries is that this epsilon is an anti-commuting parameter, and this thing actually mixes the bosons with the fermions, which is a big difference, of course. But formally, you can write any symmetry like that. Now, if you look at we say that any symmetry is a symmetry. Any such change is a symmetry. If and only if the variation of the Lagrangian is equal to, at worst, a total divergence. Okay, and if this epsilon carries my alpha indices, I put the alpha indices. Now, so this will also be a fermion. We will not even write it like this. We will write all the indices are contracted in the obvious way. All right. If this happens without using the equation for motion at this point, then you can say that there is a symmetry. In particular, the action is invariant, of course, because the action changes by a total derivative. The action being the integral of the Lagrangian, the action is invariant. And you can actually show that there is a conserved current. Conserved current is just one line. You just use the, now you have to use the equations of motion, and you say that, let me just do it in one line. So, so you also know that, so this, if this is true regardless, but you also know that well, the variation of the Lagrangian is equal to, well, you just do it. It's just chaining a rule. The Lagrangian depends on the fields and their derivatives. And so this is equal to that. Well, so yeah. Now I use the equations of motion. In this case, I use the equations of motion. And I do an integration by parts here, and I write the whole thing as the Euler-Lagrange equation. Well, I'm not using it yet, but so let me. So let's. Plus I've done nothing but putting this derivative outside of everything here and subtracting the piece that was not present here. So it's just a silly rewriting. The equations of motion are now used to set this to 0, because this is the Euler-Lagrange equation of motion. And so now you have something that looks like this, and something that looks like this, where this is equal to, of course, so right, it should be inside. And let me write it like this. So now you have something that looks like two currents. You have one thing here and one thing here, and they have, so the difference will be 0. So you got yourself the Noether current for supersymmetry. So the Noether current for supersymmetry is then, you can write it as, let's write it as S mu is going to be given then by, well, let's say epsilon S mu is going to be given by the piece that we have here, K mu, epsilon K mu, minus that guy there, dl dv mu times epsilon xa, delta x. So this is something. This is the Noether's theorem. I just wanted to sort of write it down. So this is Noether's theorem that you learn in undergraduate school, I guess. And this works just as well for supersymmetry. Absolutely no problem there. The only thing is that now this guy has an index here, because this has an index here. So it's a fermionic object with a vector and a spinor index. And of course there is its complex conjugate when I did with y to the epsilon bar. And this is called the supercurrent. Now let's have a look. So this is a nice exercise to actually do that for the most general gauge theory with kind of fields that you can think of, which is the one basically that we wrote down at the first time we met. And in their full glory, the supercurrent looks like this. Let me just write it down. It's probably good if you see it once, although it's not really something that we're going to need extensively. I claim that if you apply Noether's procedure to your theory, you get this. And I just want to write them down, but there is really only one term, or at most two, that will be relevant to all discussion. Here there's a bunch of sigmas. I guess I hope I got the indices right. This thing, you don't certainly don't have to write this down. It's just to show you that there is such a thing. Copied straight from the literature, so hopefully the numbers are right. course, you only have this guy. If you have a gauge theory with matter, you have the whole thing. And if you have just a Resumino model without gauge theory, this guy is not there, this guy is not there because this is a Turine, and this becomes another derivative. So this fella here, the first line, is actually what you get from a Resumino model. If you just replace the coherent derivative with another derivative. But this is the first, so the first exercise that you could do if you want, if you never derive this, take a Resumino model with one field, just no eyes, and derive this first line. And then take a pure gauge theory with no matter and derive the second line. No, just this piece here, okay? And then if you're brave enough, you can put it together. We've done that. And of course, Q alpha is going to be the integral over e to the x of S0 of alpha. Okay? And these are going to be the supercharges that we are considering. And of course, this theory will also have a stress energy tensor, and P mu, that's why I think down for completeness, P mu will also have will be some stress energy tensor whose zero component acts as the density for P mu, as you all know. Now, the commutation relations of supersymmetry, if you strip off one integral. So you remember we started off, the first line here was actually the Q alpha dot equal to sigma okay. Now, all of these guys are given by, they are integrals of some densities, right? So let us strip off one integral on both sides, and I can write this as, for instance, Q alpha with the, well, the supercurrent, in this case, which is the function because of that, of x equal to 2 sigma nu alpha dot p of x. With some, there is some improvement term that you make. I mean, you can go from here to here, but to go from here to here, you're actually sort of making some assumptions on possible total derivative that you can add to the stress energy tensor. But this at least shows that there is some stress energy tensor which is in the same supermultiplet as the supercurrent. So the stress energy tensor and the supercurrent belong to the same supermultiplet. Why? Because if I act on them with Q, and you can actually fill in the whole thing, you go from one to the other. Remember that we have a similar equation for phi and psi. We could argue that phi and psi belong to the same supermultiplet. Well, there was a commutator, not a commutator, but because of this. So the supercurrent and the stress energy tensor belong to the same supermultiplet. Now let us ask ourselves, suppose I have a theory with a stress energy tensor like this. Well, a theory, a Lagrangian theory, properly defined with a stress energy tensor. And let us ask ourselves, what are the possible values that this stress energy tensor can take on the vacuum? Suppose I have a vacuum theory for our theory. What is the possible vacuum expectation values of this stress energy tensor that are compatible with noise invariance? Well, there is not much of a choice. Certainly cannot depend on x, must be a constant, because of translation invariance. How do I know that it must be a constant? How do I know that the 1-point function of a field must be a constant? By translation invariance. What is the actual calculation? I act with the same, something like this. I take the derivative inside, but this becomes the commutator with P and O. But if P annihilates the maximum to the left and to the right, it has to be 0. So the derivative is 0, it's a constant. So, on the other hand, this is a symmetric tensor in two indices, and there is an invariant tensor, one is invariant tensor with two indices that we know, and it's symmetric. So this in general will be proportional to a constant, and for dimensional reason, I will write it as dimensional 4, eta mu nu. Alright? However, clearly, this is not going to go very far if you want this T mu nu to be the same T mu nu that appears in this commutation relation, and you want the supercharges to annihilate the vacuum, because clearly, if the supercharges annihilate the vacuum, so you can just replace this with this, and the Q's acting to the left and to the right would give you 0. So basically, SUSY is unbroken. If and only if lambda is equal to 0 in this case, or there is no energy for the vacuum. Okay. And this is the argument that you usually have, that basically this is in a rigid supersymmetry, this will be like the cosmological constant, and it has to vanish. The case of the supergravity is much more interesting because it's possible even to have supersymmetry unbroken, as you well know, with negative cosmological constant. But in the case of rigid supersymmetry, you can only have cosmological constant. So that's it. And now let us. So we have come up with a bunch of criteria. They're all equivalent for supersymmetry breaking or supersymmetry not being broken. Let us look at what this statement means at the classical level. Remember, even when supersymmetry was unbroken, it paid off to look at the theory with first at the classical level. So suppose we have a theory at the classical level. What do we mean by this statement, semi-classical? Semi-classically or classically? Again, the first thing you have to look at, you look at the potential of your theory. And remember that the potential of your theory in a supersymmetric theory is given by the square of the F terms and the square of the D terms. So it's the derivative of W pi squared plus, I don't remember actually the signs here, now it was in another, I mean the signs I remember there's plus, but I don't remember the factor in front. It was a half. This is the most general potential, if you forgive me for not putting in the terms that we come back to Epsilon today. This is the general potential for at least a non-abelian gauge theory that you get. And you see that in order for, so classically the zero energy is given by the value of V at the minimum. So basically, and this is again something that we started out without really spelling out in full details the reasons. This is what you should check first. So if supersymmetry has to be if at the vacuum means V minimum. It's minimum. Okay. If at the vacuum both the F terms and the D terms are non-zero, then we say that supersymmetry is broken classically. Okay. And this is actually an if and only if, because if that is true, then we cannot get 1 equal to 0, and supersymmetry is broken classically as well. So this is the first thing you may want to check. Now you start actually thinking that, oh, this could be interesting because, again, supersymmetry could be broken classically, and I guess we should probably see a couple of examples, and we will. But you should also start remembering that at least for the superpotential, we have some very strong restriction on it. First of all, and this is where we hopefully will be heading towards in the last lecture. Remember that we studied some of the properties of the superpotential, and we realized that it's actually highly constrained by holomorphism. And so, now given that the superpotential comes into this condition for checking for supersymmetry being broken or not, you can see that there is probably a nice interplay between these things. But and in fact, there might be cases, and there will be, and I hope to get to it. It will be the last part of the last lecture, where non-perturbative corrections to the superpotential actually trigger supersymmetry breaking. That is called dynamical supersymmetry breaking instead of classical supersymmetry breaking, and it's a very interesting, phenomenon. But before we do all of this,
sorry.
Yes.
So why both is not equal to 0?
No. Either. Sorry. Either. What is? Thank you. Thank you. The condition is on board. It's wrong. So, before we actually look at a couple of examples of classical SUSY breaking, those are the easy ones. Those are the easy ones because they're classical. Everybody can do classical field theory. You just there is not much to worry about. You have the Lagrangian, and you treat it with the golden rules of the 18th century, right? So not much problem there. So before we do that, however, it's probably worthwhile to state an important theorem here. And I will prove it, but in a limited case, although the theorem is absolutely valid in general and can be proven with fairly easily in the totally general fashion. The theorem is the following. If supersymmetry is broken, by the way, I probably never actually used the word spontaneously, but I should have used the word spontaneously. Take your brain or your notes and open up with Emacs, and every time I said broken so far, you should have put a spontaneously in front in the sense that we're certainly not interested in explicit supersymmetry breaking, meaning in terms where the Lagrangian itself is not supersymmetric. We're just asking for the kind of supersymmetry breaking that is realized by the supercharge not being defined on the vacuum. So when I say SUSY breaking, I mean spontaneous supersymmetry breaking. The interesting case, the only one that really is, it's theoretically of interest. In the other cases, you just add terms to the Lagrangian that by supersymmetry. It's useful. It's very useful phenomenologically, but it's not something that you want to do at this level. So when SUSY is broken spontaneously, then there is a massless fermion in the theory. Whatever you do with your theory, there will appear a massless fermion. And this fermion is called, sure enough, the Goldstino. And the ino, for those of you who don't know Italian, is what you put in, basically is the suffix for every word. If you you take a word, you put ino, it means a tiny one, a little one. And that is used in physics. You probably know the story. Was it Fermi that introduced this thing, right? And, but for the neutrino, and then but who started using it for the superparticles? Does anybody? Pauli used the word neutrino first.
Oh.
Wow. Okay. And for SUSY, who started calling inos? Nobody knows. Google.
Zumino Ferrara proprio.
Zumino. The superparticle of Suba. Okay, so right. So let me give you a proof of this fact, which is limited, a limited proof.
No, actually, at some point the neutrino was considered a superparticle.
Yes. In the very beginning, yes, there was is the neutrino the superparticle of the photon?
Right.
Yeah, and the answer was no, but yes. After, no. Limited proof. So we will do a sort of effective field theory proof. Field theory proof for the Versomino model only. But this is only because I'm lazy. But this fact could be proven completely generally using current algebra techniques by checking how the correlators behave, or the supercurrents behave as we go to infinity and so on. So this proof is just as a concept to prove the constant bosons. In fact, it's perfectly analogous. The proof is a really almost two-line proof. Remember that when you, this is something perhaps we didn't actually spell out in detail. When I have, so I'm going to consider a generic Versomino model with only kind of superfields and with a superpotential W. So I don't have to worry with Versomino model. I certainly don't have to worry about these guys. They're not there. There is no gauge. So I'm focusing on these guys. And we probably never expanded it out, but remember that this phi was equal to schematic. It was phi plus square root of 2 theta psi plus f theta squared, right? So when you have to expand this in Taylor's series, keeping the phi's as, of course, components of the sort of variables of the w's, and up to 2 orders in theta, so that you can absorb them, you can integrate them out. So there are two options really. Either you pull out an f to first order, so either you pull out an f to first order, f theta squared if you want. And this is what we have used already many times, because when we derived when we went from the on-shell to the off-shell Lagrange, then this theta cancels with this theta here. Or you can also do it, I believe there is a factor of 1/2. At the end of the day, you get a factor of 1/2 now. You can actually do to second order and pull out the psi's. And you have to use some fields in now. The factor will be wrong, so forgive me for the factor. It's just I just want to the important point is to argue how these terms arise in case somebody hasn't seen them. So you take two derivatives and then you pull out two thetas, right? Forget the square root, forget the factors. You get theta psi, theta psi. Now here this is a theta alpha, alpha, beta, beta. But of course, the thetas being only two components, you can actually rewrite this into theta squared psi I, psi j. And so what you get at the end of the day is the piece that we have already used, df, dw. So these thetas basically go away with this integral, and you get your Lagrangian, okay? So for those of you who haven't seen it, this is how you get the Lagrangian. So this is the piece that we have already used plenty of time to derive, in particular, the potential. But then you also get something that is the mass term for the fermion, the mass matrix for the fermion. Now I believe that at the end, if you do all the numbers right, you get a 1/2. It's not going to matter. So this is the contribution that you get from the superpotential. You get the F terms, it's purely scalar, and then you get this object here, which is really the mass for your fermions, okay? So the proof goes out to prove that if you have a supersymmetry breaking vacuum, this matrix must have a zero mode, must have a zero eigenvalue, okay? This is a limited proof, but it will be good enough, I believe, to show you that this is a reasonable thing to do. So how do we do that? It's really very simple. So what is the assumption? The assumption is that we have a minimum of the potential but at that minimum let's say phi 0 are the collective fields, phi 0I are the vacuum expectation value of the fields, such that V attains its minimum at that point, okay? But at that minimum, dV, dW, dphi is non-zero. This is the assumption. We want to show that the mass matrix for the fermions at the minimum has a zero mode. Zero eigenvalue. And it's a one-line group because it's right here looking at you. It's all just to do that, we just write V. We remind ourselves that V is the absolute. Well, let's write it as dW d phi I, dW bar, d phi I bar. This is what W is. If it does a minimum at some point, it better be minimized. So the assumption of that V as a minimum at phi 0 is that this thing is 0. But this thing, you see, W W depends on the holomorphic pieces, and W bar depends on the anti-holomorphic pieces. So this derivative will only hit here, it will not hit here. So this becomes your mass matrix, let's say J. So. J, which is the derivative of this guy with respect to phi j times something. And I want this thing here, this is the assumption, this thing here at some is 0 at some particular phi 0, but the other part of the assumption is that SUS is broken. That is, this guy here is not 0, because there are two ways to make this thing vanish. Either this vanishes, and this is supersymmetry being unbroken. If all of these guys vanish, then it's fine. The superpotential is 0, but there's no problem there. But there's another way to make the potential vanish, which is to make this matrix. This is a n by n, if n is the number of field of the theory. This is an n by n matrix. Is to have this n by n matrix have a 0 eigenvector, and this is here. The eigenvector is right here looking at you. This is an n vector, which is non-zero. Otherwise, all 0. And it has eigenvalue 0. So this is your 0 mode. So you have proven that this W, this mass matrix, which is exactly the mass matrix that appears here, is as a zero mode, and so you're happy. This is exactly the same way you prove, for instance, the Goldstone theorem without sort of going to current algebras and so on. It's somewhat limited in this case, but it's perfectly general. You can actually generalize. Okay. Now let us see how the supercurrent looks like before, and then we go to some concrete examples. Suppose, remember that if you still have the formula, if you have it written down or if you have it on a paper or something, remember there were these 4 terms in the supercurrent. How does a supercurrent look like? If in the vacuum, this thing, for instance, and of course the complex conjugate is non-zero, but all the other fields are 0, so at the minimum. Okay. Well, there is only one piece that survives, and it is the piece which looks like. So let me skip. Is the second piece in the expression that I had. By the way, I probably didn't say, but in the expression that I had, I used something like this. By this, I probably never said it, but this is just a shorthand for this. Sorry if I wrote it down without saying what it was. That's a shorthand. This piece is exactly the one that is of interest here. So the supercurrent then picks up one piece only, essentially, which is linear in the psi. You can actually play the. Let me get the coefficient right. You get mu alpha equal to minus I f0. So let's call this guy f, because after all, this is the maximum expectation value of the f field, f0 times of I times sigma mu psi bar I alpha. This is our supercurrent in the case of supersymmetry breaking. Now you see what the deal is. This is exactly analogous. If you remember how to write down the current for a U1 symmetry in a spontaneously broken U1 symmetry, you see something very similar, right? Remember in the Goldstone theorem, I have written it down for those of you that maybe want to sort of refresh their memory, but I'm not going to go through it now. If you write down, if you take the good old U1, the sort of it's called the Goldstone model. It's a model with just one complex field, no supersymmetry in the in the good old Mexican hat, and you write down, then there is a current, of course, associated to the U1 invariance of this thing, and if you write down the, and if you take the vacuum expectation value of the field to be at some non-zero point here, you see that this current is essentially gets to be, I put the mu downstairs, gets to be proportional to something like that name, B, some field B, which is actually the Goldstone mode of your theory, which is what makes you sort of go around this circle. So just in the same way, so if you were to try to construct a charge by integrating out the zeroth component of this current, you would get something that tries to add. You would not get something that maps one particle state into the other, but you would get something that tries to add a massless boson at zero momentum to whatever you have in your theory. This is the good old description of the sort of synopsis of what's happening in the Goldstone mode, in the Goldstone model. Here you get the same thing. If you try to construct the supercharges in this theory has a supersymmetry breaking built in. Q alpha, which is the integral of the zero component of this, sigma zero is just 1. So Q alpha is trying to add to the vacuum a zero momentum, because the Fourier component, so it's going to be minus I, f some constant times the integral of d3x of psi, right, of x. Now this is the zeroth Fourier component of psi, so it will try to add a zero momentum massless fermion to whatever states you have. And this is clearly something that does not, to begin with, map one particle into each other, because it adds one. And it adds it in a rather sickly way, because adding a massless particle and zero momentum is something that in an infinite volume is not perhaps very advisable, because you get something that is not properly normalized. So the bottom line is that yes, in supersymmetry breaking, Q is not, essentially is not well defined, unless you put the system in a box. If you put it in a box, instead of getting an infrared divergence, you get, by going to zero momentum, you get the volume of the box. So you can actually make this thing well defined in finite volume. But the analogy is the same, essentially. So this Q does not add, so does not map one particle states into each other, but tries to add something that is a bit sickly and requires to put the theory in the box. Probably the only difference, apart from the fact that this guy is a scale, this guy is a boson, and this guy is a fermion, which is the main difference, of course. Probably the only other crucial difference between supersymmetry, spontaneous supersymmetry breaking and spontaneous breaking of a global bosonic symmetry is the fact that in a sense, supersymmetry is better behaved, because by putting the system in a box, you don't restore supersymmetry. I mean, supersymmetry can actually be broken in a box. Whereas if you are familiar with the Goldstone mechanism, you know that as soon as you, strictly speaking, but this is a bit of a splitting hairs, because of course there is no infinite volume. I mean, a ferromagnet, I have a ferromagnet on my table and it's magnetized, even though the volume is not infinite. But strictly speaking, you would need infinite, or say macroscopically large volumes here to get supersymmetry breaking, because you know very well that otherwise, if the volume is finite, there are tunneling, there are instanton effects that can make the vacuum symmetric again. In supersymmetry behaves a little bit different in this respect. Supersymmetry, you can put it in a box, even a finite box, even a small box, even a zero, even a point, really, quantum mechanics, and still break it. Because it has not to do with the sort of vacuum tunneling from one vacuum to the other, but it has to do with the energy of the vacuum. So, whereas here, if you were to put things in a small box, you would restore the symmetry. Here, you can actually put it and analyze what happens even in that case. And that is why, perhaps a good way to spend the last half an hour is to do just that, and to study the case in which there is no box, in which the theory is actually a 0 plus 1 dimensional quantum field theory, namely a quantum mechanical system. There is no way, I hope you know this, I mean, from kindergarten, in quantum mechanics, forget supersymmetry, in quantum mechanics, if you have a potential like this, one particle quantum mechanics, no supersymmetry, if you have a potential like this, you write your Schrodinger equation. Well, you would be tempted, you would be tempted to say, well, there would be two minima, two ground states, one with the wave function concentrated around here, and one with the wave function concentrated around here. And then but in fact, it's not. These two, since in quantum mechanics there is a probability, so if you put a particle here, it would not stay there forever, it would have a chance to tunnel here. And it turns out that actually the ground state of the true ground state of the system is a system which is essentially a linear combination of these two wave functions, a symmetric one, linear combination of these two wave functions, which is, well, this is almost zero, but it's not quite. And this thing here is actually the symmetric, the ground state. And so the breaking of the parity symmetry. So if this one and this one were both breaking parity symmetry, x going to minus x, clearly they were not invariant. But if you put the symmetric combination, it restores, that's what I meant, it restores the symmetry here. We will see that this is actually not what happened in supersymmetry, and this is the work due to, so the name of Seidberg occurred many times in the previous lecture. In this lecture, the name of Witten will occur many times. This is all stuff that you can read from the wonderful papers of the 80s. So let me give you a quantum mechanical example of what I mean. And this is all due to Witten. So consider a particle on a line, one dimensional. And so P, X and P will be canonical conjugates. And for once, let me put an H bar here. H bar should be set to 1, but in this case, it helps us keeping track of the quantum corrections. So the classical limit would be for H bar going to 0, in which case, of course, X and P would commute with each other like they do in classical mechanics. So P, you can just think of P as minus I, the derivative with respect to X. Just ordinary derivative because there's only one X. Alright, it's simple as that. So let me introduce two objects, Q1 and Q2. That depends on a function, on a real function. Now there is no homomorphicity here. Wx is simply a function from the real to the reals. Okay, so Wx is, you can still call it the superpotential, but it's a function that takes a real, so it could be something like this. Okay. Or Ws does not have to be bounded from below, we will see, because now you can check yourself, this sigma 1 and sigma 2 are of course the Pauli matrices, and you can check, it's a trivial exercise, you can check that Q1, Q2 is 0. So they're supercharged. We can think of them as supercharges in a sense. And that Q1, Q1, which is really Q1 squared twice, is the same as Q2, Q2. And this is what I would like to call the Hamiltonian of the system, of course. And it's given by 1/2 times P squared plus W squared of X plus, see, when you write down the anticommutator of these Q's, at the end of the day, you have to, you have the anticommutator of the sigma matrices, the Pauli matrices, of the Pauli matrices, and then you end up with having to take the commutator of the P with the X. So that gives you an extra piece, which is required for the theory to be supersymmetric, which is H bar sigma 3 dW dx.
So then you need the square root.
There was a, sorry, what?
If you have here 1/2, then in Q's you need 1 over square root of 2.
Possibly. This is fixing coefficients at the Blackboard ain't my business. So let's see now what. So what can we say here? Well, so That's why W, for instance, doesn't have to be bounded from below. W could be something like this, doesn't matter. Let us assume for simplicity that W does at least that W, the absolute value of W goes to infinity when X goes to plus or minus infinity. So we don't have to worry about that. So clearly this is what should be interpreted as the potential of your Hamiltonian, right? So suppose let's look at the classical vacuum. So let's play the same game that we did here, and let's make a couple of examples. In fact, so suppose I have a W that goes like this. Then of course the V will also go something like this. It's W squared, and so there are no solutions. There are no zeros. There are no solutions to V equal to 0, and so we say the supersymmetry is broken. There will be, when in the limit where h bar goes to 0, there will be a contribution to this potential, and so this is what it is. Now suppose we do this. Suppose we take a W that goes like this. Now W that goes like this will give rise to a V. Remember, the V is the square of W. So what you get is something that goes, so it goes like this, but then it turns around, of course. Well, no, well. Okay. So we say that there is one solution, one vacuum, one SUSY vacuum. And then you can carry on. You could have two. Say something like this. Then the W should be something like this. Boing, boing. And so on. So here you would say, since this W intersects the axis in 2 points, you would say that there are two SUSY vacuum classically. Because there are these 2 points. But is it true? No, because you can actually solve this problem exactly and try to find, because you see, we want to really sort of find the full sort of play, have the H bar playing into the game as well. So let us clearly, to solve the problem can be solved exactly because we can ask ourselves, is there really a normalizable wave function such that H0, H psi is equal to 0, including the H bar as well, exactly. Now, since H equal to 0 means Q1 and Q2 equal to 0, because H is equal to this. So H is twice Q1 squared or twice Q2 squared. So this clearly is true if Q1 psi is equal to 0 and Q2 psi is equal to 0. Right? Now, is there a solution for this thing? In fact, this is what we would mean, and you can actually say that you can actually argue that this goes the other way around as well, because this guy being a positive operator, if you take a sandwich with 2 psi's, you realize that you really need Q1 to be 0, not just Q1 squared. Okay, this is because these are positive operators. So you really need Q1 psi to be 0. Now, this is also in one-to-one correspondence. You can just focus on just one, because you can go from one to the other simply by multiplying by, I believe, sigma 3. So if you take Q1 and multiply it by sigma 3, I think you get Q2, or minus sigma 3 or something. And so, really, all you got to do is to check whether there is a solution to this. A solution to this, again, can be simplified by now multiplying Q1 by 2 sigma 1. So 2 sigma 1 Q1 on psi is given by, let me get the signs right, is given by, so it's, in fact, maybe, let me even write it as, so, yeah. In fact, let me, no, not sigma 1, sorry. let me multiply by 2I sigma 1. Let's multiply everything by 2I sigma 1. If you remember what the momentum looks like, you get something like this. You get psi prime, the derivative of psi with respect to x, minus what? 1 over h bar, there's a 1 over h bar missing. 1 over h bar because this p has an h bar here. This p, if I put an h bar here, I better put an h bar here as well. So this p goes like h bar. So I put the 1 over h bar on the other side, and I write it like this: w of x times sigma 3 of psi of x. Okay? So this equation is easy enough, right? And this is a two-component equation. Right? So with psi, now since sigma 3 is a two-component, sigma 3 is of course 1 and minus 1, 0, 0. Psi is equal to psi 1 and psi 2. And we can actually, let us assume that we have, let us say that we start with a solution with some boundary condition psi 1 and psi 2 equal to 0. Let us see if we can actually integrate this thing. So this is an absolutely straightforward integration because it's just, you have to, never mind if you don't know how to do this integral, you can just integrate just write it as an implicit integral of w and look at it. So you get that psi of x is then equal to e to the 1 over h bar integral between 0 and x, say, if you choose a boundary condition at 0, w of x prime sigma 3 d of x prime times some some initial conditions, say psi 1 and psi 2. Okay, and this would also be psi 1 0, psi 2 0, and this would also be then psi 1 of x, psi 2 of x. Okay. This is my formal solution, and by exponentiating the Pauli matrix, of course, I mean this is a 2 by 2 diagonal matrix with e to the plus 1 over h bar the integral of w prime and e to the minus 1 over h bar the integral of w prime. Okay? And now you have to impose normalizability. And then you find a surprise in a sense. Well, you find the true result, which is the following. Not w prime, sorry, w of x prime actually. So this is nothing but this thing written with the sigma 3 made explicit, of course. You can just do a Taylor expansion. Now, let us suppose that, suppose you have a w that goes like this. A w that goes to plus infinity in both both ends and has 2 zeros here. Classically, you would have thought you have two minima for the potential. Classically, you have 2 v equal to 0 minima. But you soon realize that the behavior of w at both plus and minus infinity is such that none of these two guys can be non-zero. So the wave function will never be normalizable. Let's look at the behavior. Let's look at the behavior for large x very large going to plus infinity. Okay, the behavior for x very large requires, so in this case, this integral here would be very large, plus, alright? Which means that sigma 3 better have the minus component because this has to be, otherwise this thing would not be normalizable. So having the minus component means that you are not allowed to take this thing. This thing has to be set to 0. On the other hand, if you go to sigma going to minus infinity, then this integral still becomes very large, but now x being much less than 0, this integral becomes large and negative. Large and negative means that this guy must pick up a positive component, which means that this guy cannot be 0. And in other words, there are no normalizable solutions. So instead of having two minima, you have 0. Okay. On the other hand, if you had instead, so this has SUSY breaking. Okay. On the other hand, if you only had one, so like this, then you can actually check that one of these two guys survives because it's normalizable both when x goes to plus infinity and minus infinity. So the number of supersymmetry vector here is not given by the number of zeros, but is given by the number of zeros by the parity of the number of zeros. So if it is an even number, you can easily generalize this, right? The number of zeros tells you what the acceptable behaviors at infinity are. And so this guy would break supersymmetry, this guy would be supersymmetry per surface. And in general, you have either a no supersymmetry or one supersymmetry solution for the vacuum, depending on the parity, if they are parity even or parity odd, the number of zero in the states of the state. This is a simple exercise that shows you that in a sense supersymmetry is different from this is in a sense very different from ordinary symmetries, because in quantum mechanics you know that there is no such thing as spontaneous symmetry breaking in quantum mechanics. So so this was an example that I'm sure many of you have already seen. Now we actually want to start doing some examples that is a little bit more interesting for field theories, for string theories, and namely to look at field theories that break supersymmetry. So I will start in the next 10 minutes or so by going to some field theoretical examples, and we will be somewhat brief on them because on the other hand, well, I noticed the first day that not many of you had seen the alternative model, so maybe it's a good place to mention it. So this was a quantum mechanical example. In a sense, this is a bit esoteric because, as I said, there is no analog for an ordinary symmetry. We want to generalize this to classical SUSY breaking so in fact, let's say spontaneous. I never say that it's always spontaneous in classical field theory. So again, let's just say one thing. So usually, in fact, always, if you have a symmetry breaking, the symmetry breaking is a global symmetry breaking, a continuous one. It's always characterized by the existence of an order parameter, right? The order parameter is some field that takes a vacuum expectation value. Some field. Okay? Take the Gaussian model, the Gaussian model again, right? So if you have a field that transforms under the symmetries, the global symmetries of your theory, and that at the vacuum attains an expectation value, that thing breaks the symmetry. That's the definition. You can say the same thing in supersymmetry. So we will, in a classical field, we will say that SUSY is broken if and only if there is a field A, let us say, X, such that, well, A is the supersymmetry transformation of something. So first of all, this A, if we want this A to have a vacuum expectation value, better be a scalar. So I would consider this A to be a scalar, and let us say that this A is the vacuum is the supersymmetry transformation. I'm contracting the indices because I have to get a scalar of some fermionic field B. Okay. So if there is an A that can be obtained by a supersymmetry transformation of a fermionic field B, first condition. The second condition, this field is such that in the vacuum this is non-zero, then SUSY is broken. Okay? This has nothing to do with the classical thing. This could be composite fields, and in which case this would still be true. So this is actually the field theory check that you have to make. So this A, in a sense, you could think of it as the order parameter of your supersymmetry. So let's just to make sure that we are on the same length, the same wavelength, let's play a game. Let's write down all the scalar fields that we have run so far in our models. There is phi, which is the scalar universal minimum model. Then, okay, there are fermions, of course, but let's write them down as well, but it's not important because these guys, so you agree, fermions cannot get a vacuum expectation value without breaking Lorentz invariance, which is something we certainly don't want to do. So let's only write the scalars. There's phi and its complex conjugate. There is F. Right? And then there is A is not a scalar, lambda is not a scalar, and then there is D. Right? These are the elementary fields that I could possibly, scalar fields that I could possibly have in my theory and in the microscopic level. Now, suppose I have phi or a combination of phi's that has a non-zero vacuum expectation value. Can I therefore, so phi is an element of a multiplet, right? So this is a bit worrisome. But can I actually say the supersymmetry is broken in this case? No, because phi does not obey this thing. There is nothing. Phi is the first field of the superfield. There is no B such that phi is given by the anticommutator of Q with B. So this is okay. Supersymmetry can be. So this is okay. Can be left unbroken without that thing making trouble.
So what is B? I mean, can it be any of the generators that we already have, or does it have to be okay?
Usually,
one of the generators.
Right. Usually B is in the microscopic level. B is one field that you already have. Example. F is Q1 upside. This is B and this is A. Yeah. And this is the example I wanted to get to. F on the other end, and the same thing with D. D is also super.
Okay. It's a field.
It's a field, yeah. It's a field. Okay. In this case, we're only playing with elementary fields that can appear in Gamma Lagrange, and we will see that actually this is not necessary. But this is actually what happens. So F and D, which is also, we never really wrote down the transformation property, the supersymmetry transformation for D. I leave it to you as an exercise because I don't want to do it on the record to figure out what this fermion is. It's something that, of course, will include the Gruino, right? So D is also such object. So if F and D, and this is exactly what we had before, is F and D attain a vacuum expectation value, then supersymmetry is broken. We have re-derived exactly the same thing. But there is actually a more general statement now you can make, because nobody has told you here that these fields have to be the fundamental fields in the Lagrangian. In fact, this is actually the interesting, perhaps this generalizes way beyond the sort of classical level. And now it's not obvious anymore what breaks supersymmetry and what doesn't break supersymmetry. For instance, if I take, so the Gruinos are fermions, so they cannot possibly make a scalar, they cannot possibly get a vacuum expectation value. But suppose I take the Gruinos and I sum them up and I make a bilinear, say I even make it gauge invariant. This object here is a Gruino bilinear, it's a scalar. It's certainly, as far as Lorentz invariants go, this guy can get a vacuum expectation value. Does this break supersymmetry? It's not obvious, right? But in general, no, it doesn't. So this guy here, not being one of these fellas, this is okay. Yes?
Because I think that I have a wide issue. Why do you believe that if SUSE is problem, if it's false?
Right. Because because you just replace. Oh, sorry. Yes, maybe I should have said that. Put this in. If Q annihilates the vacuum, then this has to be 0. But if it is not 0, then one of the Q's cannot annihilate the vacuum.
Yeah, but then why it should be infinite?
No, there has to be a B. B, never mind B. If you can write your field like this.
Yes. And B is any.
Forget B. Yeah, forget B. If there is a B such that. The important thing is Q. If you have a field that gets a map, did you write that it gets a map? Yeah. If you get a field that gets a map, and it's the anticommutator of Q with something, then Q cannot annihilate the vacuum. when you put Q here, then it acts on the left and on the right, and it kills the right. And so this is okay. This one is not okay. This one will break through. How about the chiral condensate? Remember in QCD, remember that ordinary QCD, the quarks and gluons were made of. Remember that there is a chiral condensate, right? Two left-handed terminals can get non-zero, the quarks can get non-zero value. Now, this breaks supersymmetry actually. So if you have a super QCD and there was such a thing, then this would break supersymmetry. On the other hand, we have already convinced ourselves that the web of two such fields, phi for instance, would be okay. It better be okay because we have used these guys plenty of time in the previous lectures. These were the vacuum expectation lab, these were the objects that were giving us the measures and the values of our theories. And we didn't prove then that this was okay with supersymmetry, but it is. Does not break supersymmetry. And there we could also see because the modular space was around in modular space and so on. So, now next time we meet, I will start by discussing the two canonical examples of next time we meet, I will start discussing the two canonical examples that are on. In fact, I'll give you the option. So there are two options next time we meet, and next time you can tell me. I could spend half an hour discussing the two examples of the standard textbook examples of classical SUSY breaking, which are the Rafferty model and the variable. These are models of these are the sort of standard Weissenbacher models of classical supersymmetry breaking. And by the next time we start, I will start, if I remember, by asking the question of whether you want to see that or not. That will take about half an hour perhaps. And if many of you haven't seen it, it may be worthwhile actually. If not, we move on to stuff that is a bit, it's newer, it's stuff that maybe is less. We will start by discussing more generic conditions on superpotentials for supersymmetry breaking, for or against SUSY breaking, and other funny things that have been actually discovered not so long ago. This is in the year 2000s. On what this entails for the existence of even massless fermions and massless bosons and so on, and then and carry on with more advanced topics in supersymmetry breaking. But these two things, I need to know that you know them to some extent because they will be used as examples. So I leave it to you as a weekend homework to either study it yourself. It's everywhere. And then tell me next time we meet on Monday you don't want to see these things again. Or tell me, no, I just don't understand this thing, please go through. Depending on that, we will move on to more advanced stuff. Today I have the feeling it was a particularly... I still have 15 minutes, don't I?
Yeah.
Why didn't you tell me? I'm the only speaker. Yeah, I'm the only speaker that needs to be told to carry on. Actually, because I tend to stop earlier than necessary. But I'll stop anyway because otherwise I have to start telling you about the Rafferty model. Well, I guess I could tell you in 15 minutes. I could tell you the Rafferty model and the Ferretti model. Okay. Let's not get started. Okay. Right. So I wish I didn't spend all that time on things that I'm going to do now. All right. The Rafferty model is a non-gauged model Very easy, with 3 chiral superfields. Just 3 chiral superfields. They're called phi 1, phi 2, and x. They could be called phi 1, phi 2, phi 3, but x stands out because it's a bit special, so we call it x. And we take the superpotential V, W. We will see, it will not be obvious now why, how Professor Ferretti came up with this thing, but we will actually study then the generalizations of these things. So right now, just pull this thing out of your hat. Let us take, this is a normalizable superpotential because it's a post-cubic in the fields. And it has, of course, it has 3 fields, phi 1, phi 2, and x interacting in some funny way. Is supersymmetry broken? To check if supersymmetry is broken, I have to check the solutions for the F terms. So I have to check whether I can solve simultaneously this, which is m phi 2 plus h x phi 1 equal to 0, dw in d phi 2, which is m phi 1 equal to 0, and dw in dx, which is f plus h over 2 phi 1 squared over 2 equal to 0. Does this have a set of, does this have a vacuum? Does this have a solution? Of course not, right? Because the second equation sets phi 1 to 0, and as long as f is non-zero, now, oh god, no, sorry. Time out. F is a bad name. It's a name that is used in the recent literature because that F is a terrible thing because I use that for the auxiliary field. So it turns out that it's called F because then this F is called F because the F field of X becomes F when you solve it. But let's not call it F because otherwise you confuse it. This is not a field, this is just a couple of models. So far, let's call it lambda, psi. Give me a good Greek letter that I can use. T what? Theta.
Bacon.
Rho. There's a rational reference. Alright, so good. So Susie is broken. Yep. There is no solution to this. Now the question though is, does this guy have a minimum at all? So let's look at V. V is of course the absolute value of these 3 things together. Now you can convince yourself that V can have a minimum. In other words, V can, and now let me not do this algebra because you can have a minimum for V, which of course will not be fulfilled by setting these guys to 0, but by setting this funny 2x2 matrix, 3x3 matrix to have a 0 in the value. You can do this exercise yourself. This is simple algebra, and this is attained for phi 1 equal to phi 2 equal to 0, and x an arbitrary complex number. Okay, these are the vacuum expectation values, and by somewhat abuse of notation, I'm using the same symbol for the superfield and the vacuum expectation value of the scalar component of the superfield. That's what we always do. And so this is the solutions to this equation. It does not fulfill supersymmetry, but it is a solution. The fact that x, so now there is something here that looks kind of like a moduli space, but it's not quite. This x, so there is an infinite set of vacua. So if you were to put x in a plane like this, all the values of x would actually be of v equal to what? We can even calculate it. It's you set all the things to 0, v is equal to rho squared, right? Right? But as long as rho squared is non-zero, So this is not quite the moduli space. So this would be, let's say that V points upstairs, and now V equal to 0 is here. This is a plane of classical solutions that is not at 0. So it's not a moduli space, but it looks kind of like a moduli space. So we call it a pseudo-moduli space. It's not stable under quantum corrections. The whole point about the modular space was that we could study quantum corrections very easily by using homomorphism. But here the story is more complicated, and hopefully we will get to it. But this is it. So let me now tell you about the Ferretti-Opoulos model. Now, the Ferretti-Opoulos model, instead of having purely chiral theory, purely Versumino-like, this is an example of Versumino model with 3 chiral fields. Ferretti-Opoulos model has a U1 gauge field in it, and 2 chiral field, phi and phi tilde of charge, say plus and minus 1. This is super QED. But with a twist. Basically, we take super QED, but with a twist. We have seen this already, but we noticed that for a U1 gauge field, it is possible to add to the Lagrangian, so you could really take L of super QED. But you can add a little piece to the Lagrangian. Well, first of all, you can add there are 2 things. This was the massless case. Then I can add a superpotential, of course, M phi phi tilde. Easily convince yourself that that's the only thing you can have. This is the superpotential. But I can also add to the Lagrangian well, now the notation now is mixed. So let's say so this is the theta component. But I can also add to the Lagrangian a piece that only depends on the last. So remember that V is A plus lambda plus D. Okay, this is the auxiliary field. Now, if D is a U1, if this field is a U1 gauge field, of course it's not charged under U1. The photon is not charged. The adjoint representation of U1 is trivial. So if you act with a phase to the left and to the right, you get nothing. So these are all neutral. D is neutral as well, because the photon is neutral, the photino is neutral, and D is neutral. So you can actually add it to the Lagrangian if you want, without breaking gauge invariance. So that's fine. It's a scalar, so that's fine. And it's also supersymmetric. This piece here by itself actually preserves supersymmetry, because remember that D transforms by a total derivative under supersymmetry changes. So this extra little piece here is in fact allowed by all the rules of the game. This extra addition, however, changes the D terms of the theory, because if you remember, we have done this calculation. The D terms of the theory now. Remember, this was the very first case, the very first exercise that we did. We wrote down the D terms. I think if I dare, now I don't know if I dare writing it down, because well, it was D, it was this. Forget the electric charge, set it all to 1. Remember, it was something like this, right? This is what you get from super QED. This is the D squared term that you get from the kinetic term for the field strength. And this is the P, so this one you were getting from V alpha squared, okay? This is the one that you get from phi e to the V phi tilde, okay? And that was it. Now remember that this was the potential part of the Lagrangian, and this was the off-shell piece. I'm not sure I got the right coefficients. In fact, everything certainly has a minus in front, because you have to put a plus at the end of the day when you solve for D. When we solved for D, we got that the on-shell was essentially what you got by solving for D and putting it back, and it was equal to phi square minus phi tilde squared. And this was the one that we used to find our very first example of non-trivial modular space for the theory. Now, if I add d psi d, I still have to solve for d and putting it in. And so my solution for d simply has a plus psi here. So the potential now is given by this. Okay? Now, this doesn't break supersymmetry in itself as such, because if it was just that, I could just certainly, whatever psi is, I could take some vacuum expectation value of phi and phi tilde such that this cancels, right? If phi is positive, if psi is positive, I can cancel it with this one. If psi is negative, I can cancel it with this one. But remember that we have the mass term as well. We did put in the mass term, and that was not for fun, but it was actually required. So the full so you have to check the d terms. So the d terms are there. So the d terms by themselves would of course give you just this, which in principle can be satisfied. But if you have a mass, you also have, well, you need to set both the phi and the phi tilde separately to 0. And this is the d term, these are the f terms. So this obviously is not going to fly. And so SUS is broken. If both psi and m are non-zero. Okay. It's actually instructive, just to conclude, to look at the potential. So the potential is, of course, the potential for the d terms, which is this guy, right here. Oh, this is the d term potential. So let me just add it here. So this is the d term potential. And let me add now the potential from the masses, which of course is m squared, let's assume the masses are real, phi squared plus m squared phi tilde squared. So this is what you get when you square the f terms. This is dw d phi squared, and this is dw d phi tilde squared. Right, so this is the potential. And I just argued, obviously, just look at it, it cannot possibly be 0, so SUS is broken classically. But this potential has some fun, but it still has a minimum. Again, we're still in the condition of breaking supersymmetry, but still attaining a minimum of the potential. And here there are two cases. Consider the case where m is much, much smaller than psi. Dimensions. M squared. Psi is a dimension of a mass squared. How do I know? Because if I were to put all the coefficients here correctly, or the exponents correctly, psi is dimension 2, right? So if m is much, much smaller than psi, I certainly would like to minimize the potential. I would like to cancel this term and just pay some price here. Right? So if that is the case, then you can put the coupling constant in as well. But there is a coupling constant E, you can put E there, but this is not the point. So if psi is huge, I want to cancel this term. So I want to unbalance my phi's so that they cancel. I can either take, let us say psi is positive. If psi is negative, I can do the same thing with the other field, right? So let's say psi is positive. I want to unbalance this thing to in fact, yeah. Fine. But let's say let's put a minus sign. Okay, so let's put a minus sign and say psi is positive. I don't know why I'm doing this. So psi is, it's all completely independent. You can just flip the fields around.
So that was correct.
Yeah.
That was plus. That was correct.
Once again.
In Lagrangian, it was plus, it was correct. And then you have minus.
Yeah, I guess. Yeah. All right, fine.
And it's now minus.
Yeah, it's probably, it doesn't matter. I mean, the sign of this I can choose. So let me choose it this way, right? So that I can say that if psi is huge, then I have to cancel this term by taking a big phi. And I pay the price here. So for this thing, you can actually see that the potential looks like this. And my phi will have a non-zero vacuum expectation value. So here I break SUSY, as I always do if the mass is non-zero, but I also break the gauge loop. There is a, you can actually check if you put all the coupling constant in, there is a value in which this happens. If on the other hand, the mass is much larger than psi, and clearly I don't want to if the mass is very big, I want to set the phi's to be 0 so that I don't give this huge contribution, and I pay this little price here, that this is not going to be 0, I pay a psi square price on the vacuum. So if the mass is much larger than psi, I get this. So this is the example where Susie is broken. To check whether Susie is broken, you have to check whether the minimum is separated from the origin. Okay, so this is phi from the x phi x, and this is v. Okay, all right. So these are the two cases. Okay, and you can knock yourself out with generalizing and playing with all various things and so on. So yeah, all right. Then that at least will done the Fayelia. So you don't have the homework till next time. So next time we will start with some more, perhaps less known. This is really sort of basic curriculum of any course in supersymmetry. The next time maybe we'll do something that hopefully is not always done. Like we start off from the Nelson-Seidel criterion, and we move on to like studying a little bit the structure of the superpotential. Clearly, you realize that these are two examples, but there must be some systematic, right? There must be some way of studying these things and understanding what the dynamic is, or if you need something, build the superpotential that has these properties. So we will play a little bit with that. Okay. All right.